In this video, we take a look at chapter 2.4, which covers elementary matrices. So our learning objective for this video is to factor a matrix into a product of elementary matrices. An elementary matrix is a square matrix of dimensions n by n, or in other words, we could say of order n. And this matrix can be obtained from the n by n identity matrix by a single elementary row operation. So there are the three elementary row operations, and so here they are with examples of corresponding elementary matrices. So you could swap two rows. So in our example here, we are swapping row 2 with row 4, so you can see that the positions of the 1 in those rows have switched, and so multiplying a matrix by this E1 n by n matrix, or in this case a 4 by 4 matrix, is going to swap rows 2 and 4. So if we take E1 and multiply it by a 4 by 4 matrix, we swap rows 2 and 4 in that matrix. The second elementary row operation is to multiply a single row by a non-zero constant. So if you multiply through by 0, our row is gone, and that doesn't count as a row operation. So in this example, if we wanted to multiply row 3 by 3, we would place the 1 on the diagonal in row 3 with a 3, and that would multiply the whole row through by a constant. The third row operation is adding a multiple of one row to another row. So for example, if we wanted to add -2 of row 1 to row 3, in row 3 we would put a -2 in the first column and a 1 in the third column. That would preserve the values in row 3 and add them to -2 multiplied through by the values of row 1. Theorem 2.12 tells us that if we pre-multiply, which is just another way for saying multiply on the left, a matrix A by an elementary matrix, then we obtain the same result as if we had applied the corresponding elementary row operations to A. So if we're writing by hand, it's pretty easy to write out elementary row operations, but if you are designing some sort of computer structure or writing a function in a computer code, you don't have that handwriting ability to write out your row swaps, so you use elementary matrices. So these come up when we're doing things like designing computer graphics and how characters move. You have these different elementary matrices that correspond. Similarly, in other computer coding or for manipulating data in statistics, we use these elementary matrices to swap out and rearrange or multiply through by constants with different rows. So let's take a look at a couple examples here. So in our first example, take a look at what's happening here in the elementary matrix. So rows 2 and rows 4 are swapped. And so when we multiply through, if you want to think about the matrix we're multiplying by as in terms of row 1, row 2, row 3, row 4, you can always write this simplified notation here. Our resulting calculation, and you could verify with technology using SIMPy or some other matrix multiplication, is going to switch row 2s and row 4s. So our result here is row 1 unchanged. Let's space these out a touch more. Row 2 and row 4 have swapped, so row 2 is now -4, -1. 5 and 2, and row 3 is unchanged. And row 5 is, or sorry, row 4 is -3, 1, -9, and 1. So row 2 and row 4 swapped. What's going to happen in the next example? Well, we see down here in row 3, in place of 1, we have a 3. So that is going to replace row 3 with triple, or 3 times the values of row 3. So this multiplication works out to be -9, -8, 1. So the first row is unchanged. The second row is unchanged. And then the third row, and you can do this in your head, is going to triple. So we're going to get negative 21, 27, and 12. So it's easy enough to see visually how these multiplications work. And so in this case, we've got row 3 replacing the existing row 3. All right, in this example, we've got in row 3, we're going to get negative 2 times row 1 plus the original value of row 3. And so let's take a look when we do this multiplication, how this works out. So the first row remains unchanged. Oh, I started to write the wrong values. So the first row remains negative 9, negative 8, 1, and 0. The second row remains unchanged. And we can do this multiplication in our head. You're, of course, welcome to check out technology, but you can see if you pick this up here and multiply it here, you're going to get unchanged values there. Right? You're multiplying it through. So you can see how row 2 stays the same. All right, row 3 now changes. So negative 2 times negative 9 gives us an 18 plus negative 7. We get 11 here. And then similarly, calculating the rest of the row, we get a 25, a 2, and a negative 9. So that comes from multiplying the row 1 values by negative 2 and then adding those to the row 3 values. And then our row 4 remains unchanged. So in terms of row operations, we'd say this was negative 2, row 1 plus row 3, and that replaced, so we put the arrow here to show that it replaced as opposed to swap row 3. If we were just swapping, we would use the double arrows like we did here in the first example. So we can actually represent Gaussian elimination as a product of elementary matrices. So in our example here, we're starting with this matrix A that's an augmented matrix. And so we might say, let's use Gaussian elimination to do this. And we saw early on in chapter 1 that Gaussian elimination is really just row operations. And so we know we can represent row operations with elementary matrices. So our first Gaussian elimination here would be to swap row 1 and row 2. So we would use the elementary matrix here with row 1 and row 2 having the 1 swapped. And so you can double check, if we multiply through, we get this result with row 1 and row 2 swapped from the original matrix. All right, our next step in Gaussian elimination, so look back here and think, okay, now we're here and we want to get rid of the 3 in row 3. So our next step is going to replace row 3 with 3 times row 1 and then add that back to row 3. So that'll cancel out both of these values, right? Positive 3 and a negative 6. So we'll get some cancellation there. And so the way you do that with an elementary matrix is you put a 3 in the third row first position. That's going to multiply 3 times row 1 and then add it to regular row 3 by having just this 1 over here. All right, so we multiply through and we get these results. And so this is actually what we call a upper triangular matrix. So we've got the zeros down here on the bottom. So we're working towards our reduced row echelon form. And then our next step is we want to get rid of the 6 down here. So we can do that by multiplying row 3 by 1 6. So that's this operation right here, 1 6 times row 3 and replace that with row 3. So we've got a 1 6 here in the 3 3 position in the elementary matrix E3. And so when we carry out that multiplication, all of row 3 is multiplied by 1 6. And so we get here a matrix that's taking us a little closer to reduced row echelon form. This would just be a row echelon form here. And so You could use back substitution to solve at this point, or you could keep going to reduced row echelon form. And so the way we got to this matrix is the same as these matrix operations. So the first operation is to take elementary matrix 1 times A, and then after that result, we do elementary matrix 2 multiplied by that, and then elementary matrix 3 multiplied by that. So in terms of the order that we multiply matrices, remember, we go from the right to the left. So we start here and then work backwards. We can say that two n by n matrices, A and B, are row equivalent when there exists a finite number of elementary matrices such that we represent B as the product of elementary matrices multiplied by A. All right, let's head into Simpy and just verify our calculations over here. So I'll clear out my existing Simpy calculations, and I'm going to go ahead and enter our matrices E1, E2, and E3. So E1 was replacing row 1 with row 2. We can verify. Here's, oh, it didn't like my syntax E1 unless I made a mistake in here somewhere. I think it just didn't like my syntax. So we'll call it E. All right, it's happy with E. Then we'll have to call matrix E2 F. So we'll say F equals matrix. And that was multiplying row 1 by 3 and then adding that to row 3. So the top row here is 1, 0, 0. The second row is 0, 1, 0. And the third row is 3, 0, 1. You can verify row F. Oh, but I think I cleared by mistake. Oh, that's okay. So I'm gonna have to re-enter my matrices. Don't worry if you ever hit clear by mistake. I'm gonna move my mouse over. You just arrow up and you can re-enter your results. All right, so we've got our first two elementary row matrices, and then for my third matrix, my third elementary row matrix, I'll call it G. And so that was 1, 0, 0 in the top row. The second row was the usual 0, 1, 0. And the third row was 0, 0, 1, 6. You can verify matrix G here. All right, looking good. And then we need to enter matrix A. Which was the augmented matrix, 0, 1, negative 3, 2, 1, negative 2, negative 1, negative 5, and negative 3, 6, 9, and 3. All right, we can verify A here. All right, so let's check our multiplication. So we should be able to say G times F times E times A and get our resulting upper triangular matrix that we calculated. So voila, that is a match for what we did by hand. So you can see how if you're doing repeated row operations, you want to rely on elementary matrices if you are working with a computer. All right, in the next video, we are going to see lower and upper triangular matrices explained more in depth.